Our ancestors built civilizations around vast water sources. Ancient civilizations along rivers thrive with fertile land, resources, and most importantly, food. With that being said, Marsware employs a similar approach to humans colonizing the Martian land. Our project aims to achieve several deliverables, mainly a reliable production and secure transportation of water, an efficient water management system, as well as a continuous production of vital resources to fund scientific explorations. To explain our timeline briefly, our short-term goal would be to achieve a self-sustainable primary habitat of 100 crew members in the near future. Our long-term goal would be to explore the surrounding region to set up more outposts and colonies to expand our foothold on Mars.
Our project places heavy emphasis on ISRU, which is in short for in-situ resource utilization. Instead of transporting resources such as water, fuel, or oxygen from Earth, ISRU focuses on a continuous production of consumables on Mars. So, where do we get our resources from? This is our landing site, Deuterolinus Mensae. It is situated in the northern mid-latitude region where pure water ice can be found just a few meters below the surface. Now, let's take a closer look. We are going to land somewhere here. Welcome to our Martian city. I will start by introducing our water extraction mechanisms. This is a Rasor rover, which will kickstart our water production on Mars. It is used to collect regolith with around 8% water content to be extracted. The remaining dehydrated regolith will then be used as a construction material for our habitats. Next, this is a Rodwell rover. As the amount of infrastructure increases, it will gradually replace the Rasor rover to become our main source of water. The Rodwell works by drilling a hole past the rocky layers. Upon reaching the ice layer, hot water is jetted out from the nozzle to melt the ice layer. This will eventually create a pool of water. The Rodwell is maintained by constant heating while water is pumped into the water tank through a hose. The power input is directly proportional to the water withdrawal rate. Only 2 kilowatts of power is needed to obtain 15 gallons of water. Hence, the power provided can be adjusted according to daily water needs. Now, let's take a tour around our Martian city. This is our ISRU fuel plant, where it produces fuel for rockets using the Sabatier electrolysis reaction. The fuel produced will be stored in cryogenic fuel tanks before being used up. With this, rockets are capable of a return trip with a reduction in mass of 30,000 kilograms. Over here, this cluster of kilopowers will provide nuclear energy to meet our energy demands. For your information, each kilopower can produce from 10 to 40 kilowatts of energy per day. Over here, we have our greenhouse, which serves as a main production of food, while we have a mechanical unit beside it for repairs and construction purposes. Here, the water extraction unit is where the water will be extracted from regolith collected by the Rasor rovers. Water produced will be stored in a couple of water storage tanks. Most importantly, our habitats called Marsha are clustered in groups of 4. Water produced at the Rodwell and extraction unit will be transported to the habitats through the water distribution valve. This comprehensive water transportation method, together with reliable HDPE pipes, will ensure an efficient water system on Mars.
To support human life, an Environmental Control and Life Support System, or ECLSS, is installed in every habitat. The system is equipped with a water electrolyzer to produce oxygen from water, and a portable water processing unit to purify unused water and recycle wastewater. The wastewater is recycled in separate loops: distilled water for scientific research, consumable water, and water for hygienic purposes. This separation reduces the risk of water contamination and increases system efficiency. From these processes, excess methane will be produced as a waste product. Our fuel cell-powered expedition rovers can utilize the waste product as their fuel. During expeditions, water and electrical power will be produced by the fuel cell. As a result, human expedition missions can be sustained for longer duration and distances.
When it comes to constructing the tallest building on Earth, quantity surveyors are responsible to plan the construction costs and materials needed to minimize wastage and over budget. This concept applies to surviving on Mars with only a limited amount of water for 100 Martians, and that is where blockchain technology comes in. Blockchain technology in the water industry plays a major role in water data management and thus ensuring water sustainability to the highest level of all time. Whenever you need to have a drink or take a shower, all you have to do is tap your Martian identity card on the RFID and you are good to go. Your profile will instantly record the amount of water used, and you have to sign the receipt as an acknowledgement. This piece of data will then be encrypted and stored into the existing blockchain when every crew member submit their own water budget of the day. We choose blockchain technology instead of the traditional databases because of the enhanced security and instant traceability that only blockchain could provide. And there's so much more that we can still do about it.
How much water do we need? With the Mars wet water system implemented, especially the water recycling system, the Martian city only requires 148.64 gallons of water per Martian day to sustain 100 people and the ISRU productions. So, based on the chart that is presented, the water system is able to fulfill the demands of 100 crews living in a Martian city and also utilizing the water to generate other substances. Moving on, from the calculations that we did, only 6 launches of transporting equipment from Earth are required to build a sustainable system for 100 crews. Also, our energy budget shows our energy consumption is manageable by existing power technologies. These numbers show that the system proposed by MarsWet is able to be implemented and will succeed in the long run. For more in-depth technical details of our project, kindly refer to our PDF document.